A warm welcome to another session, Data with Nick the Greek. Today we're going to have an exciting topic. We are following up on partitions as we did already before, but now we really take a look into action, how we can apply repartition coalesce, which we already partly did previously, but now we really have a look on some use case where repartition coalesce might make sense. Of course, at the end, it depends always on the whole process. But so we're gonna go through some experience, and then you get a better feeling of the benefits, but also tricky states or obstacles you can have when repartition coalescing your data. So let's go for today. As always, we have a setup and our lovely data set with two date and timestamp columns, an ID, a numeric column, and then three string columns, of which we already saw that the first ID is usually skewed, and this one is quite uniform distributed. So before we even jump into partitioning, let's have a very short recap one more time. So while we're doing repartitioning, important thing is a good parallelization, meaning you don't want to have any of your cores in your cluster unused. So if you have 4 vCores, as we have in our case, and you execute for whatever reason a data set on only one core, meaning you have only one partition, it's not good. So usually you're gonna go with a factor from 2 to 4. If you have a very small data set, of course, rather 1. If you have a very big data set, but you're restricted on your cluster size, then of course you should increase the factor. Of course, otherwise it's gonna lead to out of memory issues. And the other thing is a good parallelization also for the side that you have a good distributed data set. Meaning if all your data is in one partition and you still follow this factor recommendation, it might happen that one of your tasks gonna run for ages and all the other tasks gonna be really fast, and then you're gonna end up with a more inefficient process than having like a clearly distributed data set. Regarding the partition size, usually people say up to 1 gigabyte, otherwise it might lead to out of memory issues or garbage collector issues, etc. Others recommend 100 to 1000 megabytes, but it always depends on your machine and so on. As an example, that's a parameter we're gonna learn later on as well. The max partition bytes when loading files is set to 128 megabytes by Spark, and depending also if you have joins afterwards, I wouldn't scratch the limits of Spark, but it really depends what additional executions you have. But somewhere in between with this factor plus 2 to 4 partitions is always a good start to see how Spark behaves. And always remember, you might have your daily batch might be small on this day. Another day suddenly you might have double the data. So if you're gonna reach the limit of 1000 megabytes already per partition and don't want to readjust the number of partitions on a daily basis, then I would rather put some safety and not scratch, for instance, the 1000 megabytes. Then the other thing is, so we learned, okay, some parallelization, more than the number of cores regarding the partitions has a benefit, but too many partitions can also lead to a distribution scheduling overhead, which we already saw previously, meaning instead of executing the data, the driver has first of all to schedule and coordinate which task is going to be run on which core, which priority, etc. And that's something you just avoid, to not have too many number of partitions. And a good hint is, well, I saw in a Stack Overflow article 100 milliseconds. So if your tasks are running below 100 milliseconds in average, or even one of those tasks, then it's a good hint to maybe reduce the number of partitions or increase, well, and at the same time increase the size of the data with one partition. So just a short recap, how does repartitioning, how does Coalesce works. So important is repartitioning is a shuffle operation. It's expensive, but it really creates a uniform data set. So that's something Coalesce can't do. With repartition, you can increase but also decrease your number of partitioning, and you can repartition also based on columns. We saw that it doesn't work always 100%, but usually for joins, it can bring a really good benefit to do this. But that's something we're gonna see later on. And Coalesce has, on the other hand, the benefit that's quite efficient. So it doesn't require shuffling. It's not a very performance expensive operation. It's a narrow transformation, but it can only reduce the partitions. And what we also saw is it doesn't reshuffle or redistribute the data. So if you have 3 partitions which are uniformly, and then you coalesce them to 3, it just puts 2 partitions together, and then you have the double amount of data. So meaning 50% of your data would be in one partition, the other 25 in the other partitions, and then you didn't reach anything because you suddenly have a skewed data set. So there are a few scenarios where you can use repartition Coalesce. Of course, it always depends on your expectation of the performance benefits. Not always it's gonna help, or is that helpful? But so the most important thing is what we already saw is you really want to rebalance your data across the number of partitions. And so let's say you have initial 7 partitions, then you can either coalesce them down to 4. Hopefully Coalesce in this case would give you some somehow a distributed or uniformly distribution across your course. If well, this doesn't work out, then you have the option of repartitioning, where you can either also go down to 4 or increase to 8, and that's something we're gonna have a look at definitely today. Then of course you might have skewed data sets, and as I already said, so one task might run longer than the others. It can also affect joins, but there are also other methods how to improve this. And let's see also how repartitioning or Coalesce can handle this today. Then another thing, join operations can benefit of repartitioning because they have like shuffling, but also other shuffle operations like order by can benefit of it by repartition based on the join key. That's something we're gonna look in a later episode into it when we're gonna talk about Y transformations. Also field operations can become more efficient. We're gonna see today. I saw it in an article. I wasn't impressed. I wasn't actually aware of it by myself, but the performance wasn't, in my point of view, very impressive. So I think that's more like a needle in all the performance improvements you can do, basically. Then you might have bigger filter operations, and that's something more like for the follow-up processes, not for your performance of the current process, but it can happen that when you filter 1,000 or 10 rows out of a 10 million data set with 1,000 partitions. The partitions don't change. They're gonna stay exactly the same, but suddenly you're gonna have, well, maximum 10 partitions where you actually have data. And then whatever following operations you have, either you're gonna save the data or you have joins, etc. You're gonna have a lot of partitions which are actually not used. And by adjusting the partitions beforehand, coalescing or repartitioning, it can really help. Then we also have the topic about, we talked about now that partitions become smaller, but we can also have the other way. So when you explode structured fields, lists, which are in your data frame, the data size can suddenly become bigger, and apparently then also the partitions gonna become bigger. And then we are again at the topic from above. don't put the limits in those cases where you know your partition size or data size can increase to the 1000 megabytes. Rather go with a lower value and allow to have like a buffer for also increasing the partition size. Yeah, and the last thing is that's something we're gonna look in the next episode, how we're gonna write data. Of course, at the end, also for writing the data, it might influence your performance on the one hand, but also how the data gonna be written. And that's really important if you have a query. So that's something we learn when loading the data. If you have a query which just filters based on one specific column, and the data is already partitioned on storage based on the column you're looking for instance, or ID first column equals 1, then Spark basically does a push down of this filter down to the file storage. It doesn't actually load all the files. But that's something really for later. It's just important to understand also that the performance and also the data distribution can be influenced by repartitioning in this case. All right, I executed the SparkUI today already for us so that we don't have to wait. And we're gonna go through now some different scenarios and use cases. So the first thing is we already saw we have, so we want to reduce the number of partitions because we realize they are not aligned with the number of cores. So just as a reminder, we have 4 cores in our cluster. And now the first scenario would be that 12 partitions is our identified target, but we have 30 partitions as an input. And what we did is we created 2 baseline executions with 13 and 12 partitions. And then what we do first is coalescing down to 12 and then repartition down to 12. And we can see, okay, the outcome is 12 partitions here already. And let's jump to the SparkUI and see how this behaves altogether for those 4 job executions. So we're gonna go to jobs. Those were the first ones which I executed. So we have the baseline for 12, we have the baseline for 13, we have the coalescing and the repartitioning. So if you're taking a look into our baseline, we have a very nicely distributed data set. It also runs performance-wise quite distributed. So those are usually the 2 important factors: distribution of your data and distribution of your time. And that's basically like our dream scenario, which we of course not always have. Also, just to have a look on the total execution time. So we can see coalescing doesn't really become way worse than our baseline scenario, or 12 and 13. But you can see that the coalescing still needs some more time, but it's 1 second longer than having 30 partitions. But what's the difference between our baseline 13, which we can see here? So we can see that's like, say, the scenario we want to avoid. One of the tasks, because we have 13 tasks and 4 cores, is running alone on one of the 4 cores at the end. So basically we have unused capacity at the end, unused resources. When we are looking on, you can't see it, but probably, but there's the recording button in the background. If you are looking on our Coalesce, what it's doing is it just puts, that's what you can see is it just puts 2 of those big partitions together. So basically, in this case, we haven't won anything if you want to have a distributed data set. Of course, we saw so now you guessed it, repartitioning is more expensive in the execution, especially the first phase with the reshuffling is happening and the data is serialized to this. Here we can see, okay, that's even a scenario which is important because we have now some spill. So that's something we should consider that, well, in this case, we would have wanted to increase the number of partitions already. So spill usually makes the shuffling really expensive. That's something we occurred here now with our number of data. But what's important at the end is that we get a really nicely distributed data set. So the second part is quite close or even faster in this case, but some operations have been done already, partly in the shuffling. But it's a similar execution time than as we have for already ready partitioned data set. As you can see here, our baseline was 14 seconds, and now we have even a little bit less. But those can be also like some slight variations. All right. Now let's have a look on our next experiment. Let's go back to your code. And the scenario 2 is now we're gonna go with, well, I brought some skew in by saying 20,001 partitions on a 200 million data set. And what we're doing is now we are coalescing and repartitioning again down to 12. So that means we are opening again our baseline 12 or baseline to 1. Then we have the coalesce. And we have the repartitioning. So let's have a look on our 20,001 data set. So you see what it means if you have too many small partitions. There's a lot of scheduling happening, and the total time across all tasks is quite high. Also, the total execution time, let's have a look here, compared to our baseline with 12 partitions, which is 14 seconds, suddenly takes nearly double the amount. What you already can see, Coalesce really improved the performance here, but the repartitioning took even longer than before. I assume repartition, the huge number of partitions seems not to be most efficiently here. So let's have a look why Coalesce is suddenly so good. Where we said, okay, it's let me just see if we open the correct one. Yeah, Coalesce 2001 to 12. So what we can see here is, as we had a lot of small partitions in advance, actually coalescing is really helpful here, because just a small pieces bring just some slight deviation in the number of rows which we have per data set. So here we have 60 million something. Here we have roughly 60 to 70 million and so on. So it's very a small percentage of deviation. That's totally fine if you can use coalesce instead of repartitioning. And so you also see in the time distribution that this is like a perfect scenario how you can improve your data set. You're just coalescing down to 12 in this case, and then run the execution, narrow transformation, highly performant, and you improve your performance here quite easily. Instead, if you're looking into repartitioning, we can see, okay, this phase took a long time, but also here. But so we have to say that in this case, I guess I have to run an experiment with a bigger cluster number on a later stage. No, actually this time we didn't have spill because we went with a bigger partition size. I just want to say probably we're gonna have spill here as well. But here we don't have spill, and still we can see the small tasks which we have initially are also there when you do the shuffling. So basically in the beginning we have to like serialize the data first of all. And afterwards, when we are loading the data, it looks like perfect. And you can also see, okay, we have some deviation here. It surprises me that the data execution takes here a little bit longer. But apparently repartitioning in this case didn't perform that well than coalescing, even if you're only looking on the second stage, which took 1.1 minutes in this case. All right, we have a third scenario. Well, where we just do the same thing, just that we're going from 90 to 40 partitions, just to see, okay, how does it behave with some intermediate partition size. So we're going back to our jobs. Let's close the other ones. So in this case, we have our baseline 40, we have our baseline 90, we go 90 to 40 with Coalesce and 90 to 40 with repartitioning. So when we are taking a look on our total execution time, again, we see repartitioning is a very expensive operation. Otherwise, we have 70 to 19 seconds, depending on our partitions. And when we are looking into our 40 baseline, we see a perfectly distributed data set. Here we have a slight deviation on the duration. You can also see it here that some bars are a little bit smaller, but our data size is distributed. Looking on the 19s, so we see that here at the end, it seems that we have some tasks which are not using all our vCores, our cores. But as we have like a distributed data set now, and we have also smaller tasks, it doesn't affect that much. But usually, usually I personally wouldn't have splitted the data that small. I would have gone maybe on 20, 50, even though we have a bigger data set here. But so we just do a very simple narrow transformation without any other side effects in this case. But going to 40 is still fair for the amount of data we have, of around I think 3 gigabytes it was. So it would be roughly below 100, but 40 would be the maximum I would go. So, and now we are doing the coalescing, and let's have a look at what's happening there. Here we already see a little bit more skew of the data. So we see the median is 444,000. Let's calculate. No, 4 million, and here it's roughly 6 to 7 million. And we see, okay, here at the end we have like one task which leaves for 2 seconds the core running by itself. I mean, I would say it's somehow still acceptable. Let's see how the repartitioning behaves. So we have the very long-running shuffle operation again, and then after the repartitioning, actually the execution is quite fast again in this case. Okay. Let's have a look on our next use case. So now, now we don't want to decrease the number of partitions, but we want to increase it. And then something which we already learned is only working with shuffling. So let's have a look what we're gonna do. So we always gonna target 12 partitions, and we're gonna start once with 1 and once we're gonna start with 10. And for that we gonna go back to our SparkUI to our jobs. And now we have our baseline 1, or baseline 10, or baseline 12, which we already know. Then we have the repartition from 1 to 12 and the repartition from 10 to 12. And you already can see what you already expected. So if you have one partition, first of all, you're gonna use only one core, meaning it takes here significantly longer than having a more distributed data set. So that's the reason why you should definitely avoid one core running, one partition running on your cluster if you're multiple cores, which you usually do. Then baseline 10 is better, but we have like two tasks which are usually then running alone, as it's not divisible by 4. And then we have our baseline 12, which seems to be the more efficient, as we have a good parallelism here. Repartitioning again is taking significantly longer, especially 1 to 12 seems to have a very big shuffle, or heavy shuffle operation. So let's have a look how our baseline 1 is looking like. You guessed it, everything is running on one core. Then what's the 10 doing? As assumed, the last two tasks are running basically alone on the 2 cores, and the other 2 cores are unused. Our dream scenario, again, 12 partitions, and it's running perfectly. Now let's have a look on the repartitioning, what's happening here. So we can see that really this one big task really needs some time. And again, we have here also some spill, as it couldn't distribute the serialization phase. And that's usually what makes the shuffling even a bit more complicated. So if you do a shuffling, we should try for those scenarios. That's something we're gonna learn also with wide transformations later on. There we should have significantly higher and smaller partitions of 100 to 200 megabytes. Then usually gonna avoid those spills. Okay, and what we forgot to check is what happens afterwards. After we did it, we have a quite good performance of 11 seconds. And the same thing here. So, because we saw 12 is our best scenario, so let's have also here, look, we have the 10 shuffle writes, also here some spill. And here we have, again, a really good scenario with a very distributed data set and a distributed duration time, and that's everything for this scenario right now. So of course something is mentioned. You see that repartitioning is highly inefficient, and for instance, if you we're gonna see where this can come in also when you're loading data. But say if you have one partition, I would even go and see why you have one partition. So one example is you have one single data. There might be different reasons, but you really should have a look on in. So the data distribution can also be a reason that you have like smaller partitions in your file store, but it's something really important. You just have a look on it. Then data skew. So to make it not too complicated, what I try to do is just coalescing down from 12 to 15 to 12 partitions, and we already saw that we're gonna have some skew there, and then we're gonna try with coalesce and repartitioning to see if we can improve the skew. So basically, what we're doing is we have the skew data set, which we all were doing coalescing 12, and then we coalesce either to 8, we repartition to 12, or we repartition down to 8 and see what the outcome gonna be. I mean, you're gonna guess it already. The Cure optimizer actually makes one coalesce out of it. But let's have a look on it. What's happening? So let's close all those experiments. Then we have the skew dataset. Our baseline is this one, and now we do a coalesce to go down. So we see here we have the skew, we have one task, or no, even two tasks, which are running here and just consuming the or 4 cores. So basically here 2 are empty, here you see 1 empty, and it's, well, looking on a whole execution, it's like 8 seconds here. If you're doing a coalesce down to 8, it doesn't really make it much better. Okay, at least at the end we are having 1 empty, but still we have here some skew also in the data set and also in the execution time. Then instead of the skew, of course you guessed it, we can use repartitioning. Let me just open it here, so we can see, okay, we have here our data set, some spill again, unfortunately, and we have here like a more distributed and execution. The same thing also for the other one. When we repartition down to 8, we also have a beautifully distributed data set, also with a distributed execution time. And yeah, we can also see 405 megabytes per partition in this case. The only thing, even if you don't want to deep dive into the SQL part yet, the only thing what I want to show here is, because I mentioned it makes out of the skew, out of a skew table which we have, which we generated with the coalesce, automatically a coalesce to 8. So let's have a look into this physical plan, what's happening here. And the most important thing we want to have a look is our coalesce, which goes down to 12. So, and now what we did is we actually executed to try to unskew it, a coalesce 12 and then a coalesce 8. And those would be like 2 operations, but the Curie optimizer is actually smart enough to just say we don't have 2 coalesce, but we just have 1 coalesce. And you see, you don't see a second coalesce operation, just see, okay, directly the coalesce happens down to 8. It's just important that even though we just did it like for dummy purposes, that this basically is totally ignored. The same thing then for repartitioning. So you don't see a coalesce somewhere in the physical plan at the end. You just see here the shuffling, which is the exchange you can see here with the round robin partitioning to 12 straight away. So basically the coalesce didn't really have an influence here by screwing up our data. But still, it shows the purpose of unskewing your data later. Okay. Now let's have a look on something where I personally wasn't really impressed about it. So I saw that you can filter or improve your filtering of the data. So what we're doing is we're having our baseline operation again. Then we take our ID and filter it based on 1000 as a baseline of the filter. Then what we do is we do a repartition beforehand and see if the performance becomes better. And do the same thing also for the ID first. and ID last column. So let's jump back to our jobs and let's find our baseline for filtering our ID, and then the same thing with repartitioning. So here we see we have a total execution time of 0.3 seconds. Here we can see we have a total execution duration of not much more actually. And this surprised me because we saw the shuffle operation on the bigger data sets usually took much longer. But first of all, you see, okay, it doesn't improve, or at least it doesn't unimprove your performance. We can also have a look here, and then we see, okay, 20 kilobytes are shuffled. All right. That's already a sign. It seems like the repartition actually happened after the filtering, that the query optimizer did there something. And that's something which actually happened, what we're going to see in a bit. Actually, I realized at the end by looking on it, because probably we ended up having one data set into one partition, but that's something we're gonna see later on. But here it looks quite okay. We have some undistribution of the data, well, which makes sense if we compare it to our baseline. If you would check now which partitions has how much number of data, we might see that's something we're gonna see in the next experiment more detailed. But we might see that some of the partitions need more filtering, some less filtering. That's why we have also some deviation, and also some of the partitions might be empty at the end. And that's what we see here a little bit more, that after the filtering, we have some skew in the partition size now. And before we jump to the next experiment, let's also have a quick look on what happened here in the background. So we did the filtering with repartitioning. Well, here you already see it. The filtering, even though we want to repartition afterwards, happened actually beforehand. So the query optimizer said, okay, let's do the filter based on 1000, and then let's do our hash partitioning based on OID just afterwards. So, and here it would be already okay, because you're gonna have a distributed database on a, well, non-unique, based on a column where we have only unique values. I mean, I personally wouldn't do it in practical cases, but at least you're gonna have like a distributed partition size. What you gonna see now when we are doing it based on a skewed column, that's the ID first. So we look on our baseline where we just filter. It's quite okay from performance wise. Here the repartitioning as usual takes a little bit longer, but you already guessed it due to the it's doing the same thing. It's filtering first and then repartitioning. As we are partitioning based on a skewed column and we are filtering out only one value, you already guessed that everything ends up into one partition. And we can see it a little bit there. Some tasks are running faster, some slower, but where you can really see it, that here it looks like fine. Okay, it's doing the filtering and then serializing the data and then shuffling to the shuffle right, but something is already odd here, because we have a few tasks which are not writing, any data, and when loading it, this happens. So what happens at the end is we are filtering out all the data from all the partitions except of one. And that's something which, I mean, you wouldn't have expected, but actually the QA optimizer does the repartitioning afterwards, and basically you skewed up your data, except of you have like concurrent operations where later on your disk, for instance, you want only to save everything into one file for whatever benefits. So there can be a reasoning, but that's something you should be aware of if you want to do some additional operations. Suddenly everything gonna be in one partition. So in this case, you could even coalesce or repartition everything down to one. It would make a difference. Let's have a look on our non-skewed. So that's something I just ran here recently. So here we have our baseline. We do our filtering. Now we have a distributed data set, so the tasks are also looking quite distributed during the filter operation. And when we are repartitioning, so it looks like that. We have everywhere some data saved, and I see this. And also the reason for that again is we are repartition based on the column. So I just want to see one value of the column. So basically all the other partitions, and we have 10 partitions in total possible anyways, gonna be again empty. And that's something we should just be aware of it. So if you have like 10 unique 10 distinct values in a column, and then you filter based on that, you're gonna end up with this scenario. So now we want to have a look on bigger filter operations. So what we already saw is our baseline, and in this case we have 20 partitions. And if a partition is, we have a perfectly distributed data set. Now what I'm doing is, well, we create also a baseline for 4, also perfectly distributed. Now what we're doing is we have 200 million of rows, and we're filtering out with 20 partitions 200, only 200 rows. What's happening is suddenly we still have 20 partitions, you can see it here, but only one partition contains data. And that's, of course, something which you want to avoid in your following processes, potentially, as we saw already on the previous experiment. And I mean, you have the option to do coalescing, but coalescing doesn't really help, because you see it here, it's still the same result if you coalesce down to 4, because it just brings the empty partitions together, and this doesn't help anything. Meaning repartition would be here your way to go if you want to redistribute the data, either based on the column or only based on the number of partitions you want to have. So, and now here I think there is no need to jump into the SparkUI, but the last thing we want to do is to just have a look on another following transformation action, in this case count, what's happening if you are doing a filtering. So we take here our baseline, which is the count for 4 partitions, the count for 20 and for 4. We also see that it's counted perfectly. And then we apply our big filter, once without Coalesce and Repartitioning, then once with Coalesce, and once with Repartitioning. And now let's see how this looks in the SparkUI. So our baseline count looks like that. So we have 50, let's have a look on the performance first of all. So we have 70 milliseconds for the count here. If we do the same thing with 4 partitions, we're a little bit faster. This is probably a little bit too many partitions, but we always have a little bit of scheduler time in those cases. Then if you're doing the filter or counting is really fast, because what the QR optimizer is doing is filtering down the data. We have less data to count, so each operation gonna be faster. And that's already one interesting part. And then our Coalesce and Repartitioning is pretty much the same. It doesn't change much in the total duration. But I mean, this also shows less data counting and any other operations gonna be coming fast. It also shows that when you do any operations, filter first before you do any other operations afterwards. This counts also for columns, but that's something we're gonna look later on when we are looking on how to load data efficiently. Okay, so let's have a look on how our baseline looks like. So we have 20 executions. Here we have some scheduler delay. As assumed a little bit, we have some distribution also when counting the data. So it's a little bit skewed, the execution time. And then what we're doing is we're just reloading all the 20 rows which we have, and re-executing our count here. So we have 1 row per core who calculated 1 subsequent count. Having a look on the count for 4. Wait, let me check. No, that's our baseline, which we want to have a look on. It looks pretty much the same, just that it's a little bit more distributed here. Now, what we want to do is have a look on our filtering. So remember that after this filter, we just have 1 partition actually with data, and it still looks like that. So basically, it still needs some execution there, even though most times you don't really have any data. So the subsequent row is gonna be basically 0, and that's something. I hope I'm not saying nonsense here. That's something we should also be able to see here. So baseline count with filter, that it first filters, and then we have our exchange regarding the count, which you can also see in the SparkUI. We have our filter here, filter everything by 100, and then we have our count, our partial count, and then our final count here. Then now let's see how Coalesce or Repartition might behave in this scenario. So we can see we have the Coalesce definitely in the first stage. So that means we are counting after coalescing. So you can see now that we have like a nicely distributed counting experience now. And also, like when looking on the second step, 4 milliseconds is quite efficient. Let's have a look what it was with our baseline count with 20. It took longer. So basically, by reducing after the filter operation, the coalesce, it already improved a little bit the performance. So now let's do the same thing with repartitioning. So let's have a look what's happening there. Of course, we have now 3 stages. The first is the repartitioning part, which you're gonna see here, and then we have here the counting part afterwards. Also here you can see the duration for the counting became a little bit better. Here we have it a little bit skewed, so it seems like coalescing helped there more, but remember that we had a skewed data set, so if you go performance-wise, you don't see a benefit, but if you want to look on the data skew, which we have, we now have here like a more skewed data set. And then you see here we have 50 rows which are coming in. Like on the shuffle operation, you can see it. And then we're just saving the 4 rows, which you can see here at the end. And let's have one more look also here, how the coalesce count behaves. So we have our coalesce and then our exchange for the count. So basically our assumption which we had can be seen here. We filter, we coalesce, and then we count. And the same thing also for the repartitioning. So we filter, then we have our round robin partitioning. So our repartition basically. And then we have our counting here. All right, that's pretty much it for today. Just before we finish up, like 2-3 small comments. So what's really important is whatever you do, you have to balance the performance of the current process versus the data distribution. So maybe Coalesce might help you to have a good performance, or even don't do it. And even if you have only narrow transformations, but the distribution of the data might influence your following processes. For instance, any queries on the data. So if you repartition your data, we see it, for instance, with delta latest there more efficiently. How if you distribute the data on storage properly by columns where you usually filter, you can have a significant performance. So it's not only consider the current process, but also the following processes. So the second thing is, even if you deep dive here, some operations that you see might not always make sense, and might only realize very small execution improvements, and is it worth to invest hours to improve your performance by 10 seconds? Usually not. But if you have realize with a small amount of data, your process running like for 3 hours daily, for instance, and you can reduce it by down to 50 minutes, it's worth to improve. And I mean, despite that, something which doesn't cost a lot of time is just have a quick look into the SparkUI, see if too much driver memory is consumed by whatever operations like collect and Spark, or any Python, non-PySpark, but Python operations with pandas data frames, for instance, create some memory. Later also I'm gonna make a video on that. Are all cores used as we saw? If you're not using the cores properly, or even use just one core for whatever reason, something you should improve. We had even a process where we realized it on our side recently, and could improve the speed by that. And do you have spill on the disk? So we saw with repartition we had some spill on the disk. Sometimes you can accept it if the outcome is valuable, but especially doing join operations or wide transformation, we're gonna see that avoiding spill to this can really improve the performance later on. And with that, thanks a lot for listening to this long session today. If you like the video, feel free to like it, or to comment if you see some things different, and of course subscribe the channel. And we're seeing each other soon for writing data and how partitions behave on that by interacting with our file storage.